This is the board that I'm using, so if you want to want to purchase it and program it and play with it yourself, the price is significantly cheaper than I was anticipating. It's only $9.99 from the manufacturer's website, microchip.com. My Canvas is not working on this computer right now, so I can't put it in an announcement quite yet. I will do that when I get back to the office. But if you want to purchase one of these boards, you're more than welcome to do so. When I purchased this one, they were $25, so they've come down in price quite a bit. But it's the AVR 128 DA48 Curiosity Nano evaluation kit. But when we left off, we were looking at the blinking LED once per second problem, and the LED wasn't blinking. It took me a little bit to figure out exactly why. All the code that was in there was right, except for one little thing. This line of code right here. SEI, enable the global interrupts. See, the interrupts, there is a there's basically three things go into triggering an interrupt. First of all, the condition that causes the interrupt, in this case, the overflow of the timer. The condition, the peripheral interrupt enable, and the global interrupt enable. In essence, these three lines go to an AND gate, and if all three inputs are high, then the interrupt gets triggered. So three things are necessary to trigger an interrupt: the condition, the peripheral interrupt enable, and the global interrupt enable. Now, I did enable the peripheral interrupts here in the code. What I forgot to do was put in the enabling the global interrupts. They were not enabled, so the light was not blinking. I put in that one line of code, and we have a blinking light. So that was all that was necessary from the code that was given, entered in. So the lines of code that the instructions that were used in this program are the LDI, STS, RJump, CLI, exclusive OR here to toggle the interrupt or toggle the pin, and SEI for setting the global interrupts, and RTI to return from an interrupt handling routine. I will also put this file on Canvas in the Files section, so you can look at it in more detail. I've tried to comment it. Appropriately. Let's see here. Let's put the comment in here. Enable global interrupts. But yeah. The structure of the program is fairly simple. The first section is the interrupt vector table, which you define where what interrupts you're going to be using and the interrupt handling routines, where the interrupt handling routines are for each of the interrupts. The start routine, which initializes the program, which initializes the clock, the interrupt vectors, configures port C pin 6 as an output, set the period of the clock overflow, and enable the interrupts for the clock, enable the timer, and the line that I forgot, this enable the global interrupts. The main loop just does nothing, and no P is no operation, and it just jumps from the loop, jumps from here to the loop label. The interrupt handling routine disables the global interrupts, loads the, turns off the interrupt flag that brought us here, get the value of the out register of port C and XOR it with 1 and bit 6 to toggle the pin, and then store it back to the out register of port C, re-enable global interrupts, and then return from the interrupt handler. So, a total of almost 150 lines of code to blink an LED once a second. So, yes, assembly can be tedious, but you do have control over every bit in the processor. Kind of a gives and takes type of thing. Give you control, takes away programming speed. But we are going to do, this is going to be due after midterm next week. We are going to have a programming project where a potentiometer is going to be used to vary the speed of the blinking light. So that it will be your first programming project for the semester. You can use this as this program as a framework. Like I said, I'll put it up on Canvas in the files section. You can download it, look over it, use it along with the instruction set summary or instruction set manual that's also in the files section of Canvas, and you can get more in depth as to how each instruction works. Each instruction is very simple. Like I said, an assembly instruction does one thing only. In 99% of the cases, there is when you in like C++, you execute a command. It often does a series of commands and gets expanded out in machine code into dozens, if not hundreds, of lines of code. With assembly, each line of code does just one thing. The simplicity of it makes it challenging to use because most people don't think in simple terms like that. We have complex lives. We see complex computers in front of us, and we assume instructions will do more than one thing at a time. Assembly code is very simple. It doesn't do lots of different things. But now we're gonna, let me go ahead and go to documents, class files, spring 2026, computer.org, the data sheet. Come on, there you go. So going back to the data sheet, we are going to be using the analog to digital converter to get a value from the knob to indicate to vary the control of this blinking LED. Now, does everybody in here know what a voltage divider is? How a voltage divider works? I see one nodding head and one shaking head. Okay, let's go ahead and cover that real quick. A voltage divider is essentially two resistors in series. And say we're having 3.3 volts here. You do remember this? Okay, does anybody not remember what a voltage divider is? Okay. Okay. I'll keep breaking it down. Yeah, this is in series. Two resistors in series, and this is R1 and R2, and the output equals let's see here. It's R2 over R2 1 plus R2, right? Yeah. R2 over R1 plus R2 times Vn. Okay. So you can, so this voltage out, depending on the value of the resistors, is going to be somewhere between 3.3 volts and ground. If you make this a potentiometer, you make it a variable. You can turn the knob and change the value of the voltage coming out. So that would look like this. You got we're going to use 3.3 volts for this, and a potentiometer to ground, and the output is the center pole, equals 0 to 3.3 volts, depending on the position of the knob. So that's how we're going to get an analog signal. That is an analog signal as opposed to digital, which is just 3.3 or 0 volts. The analog to digital converter, let's go back to come on, there you go. The analog to digital converter, or ADC, is section 31, has 12-bit resolution. So the what is that? 4096. 12-bit resolution is a value. Will give you a value from 0 to 4095. Okay. Just as a comparison, CD quality sound is 16-bit resolution. It's much higher resolution than this is. Whereas old landline telephones were 8-bit resolution, so less resolution than this. That's why the sound quality wasn't as good. The sample rate, 120 or 130 kilosamples per second, is considerably faster than CD quality audio. CD quality audio is only 44.1 kilosamples per second. So this is just kind of a middle of the road type of analog to digital converter. We're going to do just single-ended conversion as opposed to the difference between one input and another. We're only using one input, so this doesn't really matter. We're going to do free running, so it's constantly sampling the consistently sampling the potentiometer output. We're not going to worry about accumulation. We got to select a voltage reference, which is the power going to the chip. Not doing this temperature sensor. Programmable input sampling duration, not worried about that. Threshold and window comparator, don't need to worry about that. We're doing free running, so we're not doing event-triggered conversion. And we are going to use the interrupt conversion complete. Rail-to-rail input voltage range just means it's the full range of the from ground to the reference voltage. So that's what we need to look at for that. And we went through that already, the overview of it. One thing that the features didn't mention was the option to left shift the results. The sample range is only 12 bits. The period register of the clock is 16. So you would have 4 bits. If we just transferred the conversion over to the period register, the 4 most significant bits would always be 0. It wouldn't give us a full range of what's available on the clock. So, knowing that this is this can be an issue, when you go to the register summary, control register A, bit 4 here. Writing 1 to this bit will enable the left adjustment of the ADC result. So the most significant bits will be occupied by the result from the ADC, and the lower 4 bits, the least significant bits, would be always 0, giving the impression of a range from 0 to 65,535. So we'll use that left adjust feature of the ADC result register. So while we're at the control register A, we can see that bit 7, run and standby, we don't need that, we can leave that 0. Conversion mode, single-ended. Like I said on the features, we're going to be using single-ended, where we're just reading the value relative to ground. So leave that one as 0. We are going to left adjust, so we have the full range of the 16 bits. The resolution select, we're going to select the 12-bit resolution, So that's the default of 0, 0. We're going to have in free running mode, so the first conversion is started by writing a 1 to the start conversion bit in the command register. And then it will, as soon as the one conversion's done, it will start another conversion. Go as fast as it can. And finally, enable the ADC. So we're going to set the bit 4, bit 1, and bit 0. The rest will be zeros. So going back to the, let's see, Control A, 0, B, 0, 0, 0, 1, 0, 0, 1, 1. Setting those bits and leaving the others cleared. Let's go back to the rest of the initialization. Let's see. Okay, initialization. Come on. Catch up. Initialization. Configure the ADC voltage reference on the voltage reference peripheral. Come back to that. Select single-ended or differential mode in the Control A register. Configure the resolution in the Control A register. Configure the left adjust in the Control A register. We did that. Free running mode. Selected that. Configure the number of samples accumulated. Not worried about that, so that's optional. We don't need to worry about that. Configure the ADC clock. Don't need to worry about that. We'll just have it run as fast as it can. Select the positive ADC input by writing to the multiplexer position bit field in that register. Don't need to do the negative ADC input value. And finally, enable the start event by writing a 1 to the start event bit in the event control register. Oh, that's optional. Enable the ADC by writing a 1 to the ADC enable bit in the Control A register. We already did that. And then finally, go back to the register summary. The mux position, the mux position, multiplexer position. We're going to use the AIN analog input 0, which is on port D pin 0. So we can leave that as 0. We don't need to set that. And then the command start conversion. Writing a bit will start a conversion as soon as any ongoing conversions are completed. In free running mode, this will start the first conversion and will read a 1 as long as a conversion is in progress. That's the basics of the ADC. And the voltage reference, it made reference to that in the first step of the initialization. The voltage reference, it has a reference for analog to digital converter 0, and it supports the following voltages. We are going to do VDD. So the voltage reference for at the ADC 0 is going to be 5. And we'll make this always on. So what's a binary for 5? Huh? 101. So 1 in the 7 bit, 1 and 2, the 2 and 0 bits also set. So I'll go back to this, and VREF will be 0B 1 0 0 0 0 1 0 1. Setting those individual bits. Now, if I'm recalling correctly, I just remembered this. Somebody asked me about when to use binary and when to use hexadecimal. And how do you know when to use which? Well, when you're setting individual bits, it's easier to write out a bit field in binary than it is to figure out which bits are what in a hexadecimal reference. Memory locations are typically use the hexadecimal format. Hexadecimal is well, memory locations in this processor are 16 bits, which is only 4 hexadecimal digits. Writing out 16 ones and zeros is impractical, whereas writing 4 hex digits is a lot easier. But for bit manipulation, using a bit field with it prefaced by the 0B is a lot easier, and it's easy to see what means what. Does that make sense? Okay. Let's see here. Let's look at the base addresses, thinking about that. The addresses for the VREF. VREF is going to be base address, what was it? 00A0. And the ADC base address is 0600. So those are the two addresses that you will be using as the bases for setting and retrieving information from the peripherals. So, any questions about how an ADC might work, or how this will progress? I will have a schematic diagram of the circuit available next session. I need to draw it up real quick. Yes. You do not have to buy one. I can, you can submit your programs. I can compile them on my computer and run them on my board to test them to see if they work, and give you feedback if they don't. If you turn in the programming assignment early, I will be able to test it and give you feedback. If it doesn't work, you have time to fix it before the due date. Yes. 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 Monday we're going to have a review of what we've covered so far for the semester. I was thinking about doing that Friday and Monday. And the midterm will be on Wednesday. Friday there will be no class. Friday before spring break, give people a chance to head home, head to Destin or Tampa or wherever you might be headed for spring break. So next week will be a short week. Just the midterm on Wednesday, review, and that sort of thing on Friday and Monday. And somewhere in there I got to write up the midterm exam. It'll be necessarily short because this is only a 1 hour class, so they can't have you in here for 2 hours taking a midterm. But does that sound like a reasonable schedule? All right. I see nods. Okay. Well, we will adjourn for the day. Have a good day. See you on Friday.